This is lecture 5 for this quarter, and this lecture covers the scientific method. So before I begin, let me just say that as meteorologists, we want to know what we know. And we want to make sure that what we know is accurate. And in order to make sure that we know that what we know is accurate, we have to do science. We have to do studies. We have to figure things out by doing experiments. And so that's what I'm talking about today. So for today's goals, I want to make sure that you understand how scientists draw their conclusions. I also want to talk about a misunderstood word, real quick, theory. And then I want to talk a little bit about science to pseudoscience. And then I'm going to end class today, or in this lecture today, with a little bit of just a recommendation, a little bit of a something I would recommend that you do. And that is to propose a simple scientific experiment. All right, so let's talk about what science is. So science isn't a subject in school. Science isn't hard. Science isn't a lot of the things that you probably thought it was. And what I have over here is actually kind of a stereotype of what science is. It's not a madman in a laboratory with bubbling chemicals. What actually is science? Well, science is the study of the world around us through two things, observation and experimentation. In layman's terms, science is the study of everything. So think about everything we know on Earth. From 2 + 2 = 4 to knowing what a schema is in psychology, or knowing that air temperature is the highest in the afternoon, or all of the things that we have taken for granted in life have actually been concluded by science. And this doesn't just include the hard sciences like biology, chemistry, physics, and so on, but this also includes history, political science. This includes all of that. So science is basically the study of everything. It's a quest to understand the world around us. So believe it or not, you are a scientist. And in fact, for the remainder of the quarter, I want you to do me a favor and tell yourself that you are a scientist. That it may seem like science is your hardest subject in school, but actually you are a scientist. You do science every day and you don't know it. And so don't feel intimidated by this. This is actually really cool stuff. So science is done one of two ways, and we all do this. Observations and experimentations. Observations are simply just looking at how something behaves. You don't change anything with it. You don't manipulate it in any way. You just sit back and watch it happen. That's what observation is. So making measurements, measuring air temperature, measuring wind speed, or making a measurement of body temperature, or making a measurement of how many college students wear headphones to school, or those are observations. You're not doing anything, you're not manipulating anything, you're just observing. On the other hand, another type of study that scientists do is what's called experimentation. Here you make a change and you observe the outcome. Believe it or not, weather forecasting is an experiment. When we make weather forecasts, we actually use what's called a model of the atmosphere. Meaning we take all the complexities of the model or of the atmosphere and we shrink them down into a model that we can then analyze. And we can make changes to that model, we can tinker things, we can change data, and all of those things then give us an outcome. And we look at that outcome, and that's our experiment. So weather forecasting is a type of experimentation. Another good type of experimentation, let's say you wanted to monitor or experiment or figure out how does tutoring affect success in school. Well, what you could do is you could take a class, split it up into two halves. One half of the class isn't going to have tutoring, one half of the class is going to have tutoring. And then give them a test and see what the outcome is. So that's another experiment. Basically, you change something and you observe how it changes. Now, science is done via a framework that's referred to as the scientific method. And I'm sure many of you have heard of the scientific method in your life, so I'm not going to really talk about it a whole lot. Instead, what I'm going to talk about is how it's not nearly as clean as it looks. So, the scientific method is a sequence. It gives us a set of steps that we use to do science. And there are 6 main steps. The steps are identify a problem, propose a hypothesis, test that hypothesis using an experiment. Once you test that hypothesis, you're going to have data. That data are your results. You then analyze those results, and based on those results, you draw a conclusion. So you identify a problem, propose a hypothesis, design an experiment, organize the results, analyze the results, and then draw a conclusion. That is how you do science. That is what science is. Doing those 6 things. However, contrary to popular belief, science isn't restricted to just those 6 things. Instead, the scientific method is very flexible. For example, let's say you're doing an experiment, you propose the hypothesis, and then you find out, I really can't test this hypothesis. There's no way I could prove this to be true or not. So you then have to go back and come up with a new hypothesis or come back and start working on a new problem. Another thing may happen, such as you do an experiment, you get the results, and you find something that you didn't expect in the results. And let's say that the results still answered your question and you still proved your hypothesis and everything, but something interesting came out of the results. Well, that can spawn a new experiment and a new step. You could also have something where you identify a problem, you begin to put together your experiment, and then you run out of funding. And in order for you to then carry out the experiment, you have to then paint the problem in a way that you're going to get funding. So then you do that, you go and you get the funding, but now you have a new experiment. So there's many different things that could really influence the scientific method. And so it's not, it's not always it has to go like this. This is just how it's organized. Discoveries happen on accident. There's all kinds of things that can happen. So it's very flexible. And what I'm showing here, this is what's called the activity model of the scientific method. So rather than viewing the scientific method as a set of very stringent sequence steps, you can actually look at it as something where you're doing all of these different things all at the same time and all at different times, but the center of the scientific method is questions. You're seeking to answer questions. But you can bop around between one step and another step all the time. It's very common. It's very common. So the scientific method is much more complicated than we can set it out to be. And in fact, the only way that you can really model the scientific method is by actually carrying out experiments, by actually doing a study and finding the means to do the study, having peers come in and evaluate the study, and then they tell you to do something different, answering questions about the study, and so on. So there's a lot going on in the scientific method. Now, with that said, there are some terms that are thrown around in science that I think a lot of students actually convolute with one another. They actually confuse with one another and maybe even use interchangeably. And in fact, I wouldn't just say students, I'd say the overall world is really guilty of doing this. And here are 4 terms that are commonly misunderstood for one another, and so I just want to briefly talk about them. They are hypothesis, theory, law, and fact. So let's jump in and talk about them. So, what's the difference? Well, first let's talk about theory versus hypothesis. Theories get a bad rap, and I'm going to explain why in a moment. So, both theories and hypotheses belong to one family. They have one thing in common. They are explanations of why something occurs. So, for example, the sky is blue. That's not a theory. That's a fact. But why is the sky blue? Well, I could propose a hypothesis that could explain why the sky is blue, or I could look up a theory on why the sky is blue. So what they have in common is they're both explanations of why something occurs. So a theory or a hypothesis could explain why the sky is blue. However, there's a big difference between theories and hypotheses. A hypothesis is, I'm sure that you've heard this phrase before, it's an educated guess. However, it's based on previous work, it's based on previous things that you're now applying to this particular situation. Basically, you're saying, well, we know that from other studies that this, and this happened. Well, applied to our current situation, this is what would happen. Basically, it's an educated guess. However, it's not proven and it hasn't been tested. And so a hypothesis is basically a guess. Again, it's an educated guess, but it's a guess. Now, this is important though. Hypotheses are good because they then give you the idea, or they give you the way to approach an experiment. The purpose of any experiment is to prove a hypothesis. Now let's say you do an experiment and you prove the hypothesis. Well, then the hypothesis gets upgraded to what's called a theory. So a theory is a tested and proven explanation. It is accepted as true. So a hypothesis is untested, unproven, no evidence. Yet it's just based on previous studies. A theory has now been tested and proven. It is accepted by the scientific community as true. A hypothesis becomes a theory once it's been proven by an experiment. Well, here's the thing. Have you ever heard the phrase, it's just a theory? Or, oh, I have a theory. Or people use that phrase all the time and they don't understand what it actually means. A theory is not a guess. A theory is not just something that you pull out of your brain. A theory is actually something that has been well proven, that has actually been tested, and accepted by the scientific community. So theories actually have a lot of backing to them. They're not just willy-nilly guesses. No, those are hypotheses. And I've actually found myself, the longer I've taught, I've actually had to train myself to say, rather than to say I have a theory, I now say I have a hypothesis. Now, if I test my hypothesis and I prove it, then it's a theory. Now, what about laws and facts? So theories and hypotheses explain why something happens. Laws and facts, on the other hand, actually explain what something is or how something behaves. So theories and hypotheses explain why. Laws and facts explain what. So a law is a generalization of how something will behave. So rather than making a different rule for 100 different scenarios, a law basically bunches all those scenarios up into just one generalized, like, this is what happens. Examples of this, Newton's laws of motion, and so on. Now, laws can actually be broken in certain situations. For example, Newton's laws of motion actually don't apply when the motion is really, really tiny, or the motion is happening at a speed close to the speed of light. In those cases, Newton's laws break down. However, in practically any other situation, Newton's laws are good. They work. so we can't discard them. They're just a generalization. However, there are going to be exceptions. A fact, on the other hand, is indisputable, objective. It is true, always, always, always. 2 plus 2 is always equal to 4. 2 plus 2 is always equal to 4. If I have 2 things and 2 more things and I put them together, I've got 4. That is a fact. The sky is blue. That is a fact. If you want to call it something else, it's still blue. It's still blue, it just you called it something else. But it's indisputable, it's objective. 100 people out of 100 people know it to be true. So that's the difference between a law and a fact. A law is a generalization. A fact is indisputable, objective observation. And again, these explain what something is. Hypotheses and theory explain why something is. Now, the last thing I want to talk about in this class is really based on some stuff that's been happening quite a bit lately. Science versus pseudoscience. So, and I'll give an example in a moment. So, when we make a theory, how do we know that that theory is valid? And I'm going to talk about a lot of theories in this class. I'm going to talk about a lot of different things. How do we know everything I'm saying is true? Well, a scientific conclusion is valid. A theory is considered good if it is based on substantial amounts of data, meaning we didn't just look at one instance, we looked at a bunch of instances, applies in multiple situations, can be tested and reproduced by other scientists with the same results, meaning if they do it the same way we did it, they get the same answer that we get. These things make scientific conclusions valid. So they have a lot of data to back them up, they can be applied in multiple situations, and they're reproducible. So this is important. You can't make a scientific conclusion based on just one data point. You can't make a scientific conclusion that only makes sense in one case, and you can't make a scientific conclusion that only matters in your particular setup. Nope, it actually has to apply these things. And pretty much everything we're going to talk about in this class is scientific. It has been tested and proven time and time and time again by science. I'm not going to throw things at you that are still controversial. On the other hand, pseudoscience and conclusions that are made based on pseudoscience are based on very little data. In fact, in some cases, even just 1 or 2 data points, based in a very specific situation, and conclusions are based on questionable, if not flat out, just wrong methods. Things just weren't done right. So in this case, you would get a very different outcome if somebody else did the same study. You would get a very different outcome if somebody used a different technique. It's not reproducible. It's only one specific situation, one data point. Basically, it does not apply globally. So let's talk about science. I don't mean to bring up something so controversial early on in the course, but it's just fact. The Earth is warming up. This graph that I have here represents changes in the average temperature of the Earth. And if you actually take a look, the average temperature of the Earth has varied from roughly 56.5 degrees to closer to 58.5 degrees. So it's varied about 2 degrees in the last roughly 120 years. Well, this data, this conclusion, is based on data that's taken from tens of thousands of locations over many years, all using the exact same globally accepted methods of data collection, meaning that the temperatures were taken the exact same at all the different locations, and then averaged together to produce one temperature for each year. And these this graph, these results, have been replicated by many different scientists. So this is based on a lot of data. This is based on many different locations, so it actually can be applied over many different locations. It's been analyzed, and these same conclusions have been drawn independently by many different scientists. On the other hand, what about pseudoscience? So, not to get political, but our president, Donald Trump, has posted on Twitter several times, hey, it's snowing, global warming must be fake. There's another example of a senator who actually brought a snowball in from outside into the Senate chambers and said, hey, look, global warming is fake. Here's the problem with that. Their conclusion is based on one day, in one location, one data point, not done using any objective methods. Basically, they say it's cold, global warming must be fake. And there's no actual data. Well, here's the thing, and let me give an example of this. So this is Donald Trump here talking about snow in Texas and Louisiana. This happened in January of 2014. January of 2014 was a very cold year for much of the eastern United States. However, if you came over here to the West Coast, it was actually very, very hot. We actually experienced record heat that year. So, how is that fake? You can make a completely different conclusion based on where you're at. This, right here, isn't made on a different conclusion based on a different location. This has been done many times, many scientists, using data collected from all kinds of places. This, one location. And also, I mean, I hate to say it, but done by somebody who doesn't really understand science. It ignores other things that are taken into account. And it's not, there's no quantitative data, there's nothing like that. So, just to warn you, there's a lot of stuff out there like that, and this is fake news. So if you've heard a lot of fake news lately, this is fake news. It's just based on poor science. There's been no proper conclusions done. And in this class, I try to avoid stuff like that. So I try to use facts. I'm going to show you data. And don't worry, it's not going to be anything scary. But I'm going to show you conclusions that have actually been driven based on sound scientific studies. So just to review, science is the study of the world around us. It's done via observations and experimentation. The scientific method is flexible. Theories are our misunderstood friend. They are tested and proven. Theories have a lot of support. Hypotheses, not so much. Laws, on the other hand, those are generalizations, while facts are indisputable. And then science is based on many observations, taken over a long period of time and reproducible by many other scientists, while pseudoscience just isn't. So that's it for now. I'm going to do a video for our module activity this week when I talk a little bit about weather maps. But other than that, I will see you in the next module. I'm Terrence Mullins. Thank you for watching.